Alright, so this is a recording because I have to record today's lecture because I have meetings at the usual time when we have a synchronous session. So the good thing is you can watch this anytime you want to, and then the bad thing is it is harder to ask questions. So I do encourage you to watch this as soon as possible and ask questions. And if you want to ask questions over Discord, the best way to do it is to screenshot the question itself. You screenshot the context where you ask the question, and then go ahead and post the question itself. All right, so let's go ahead and start with the scope of the exam. The previous exam, in exam 1, we are basically done with everything related to functions, but we didn't test anything about aleph null. So that means aleph null is in the scope of the second exam. Relations is definitely within the scope of the second exam. And then propositional logic is also within the scope of the second exam. You might want to locate those the videos corresponding to those topics and review both by reading the content that is already written in not PDF, I don't do PDF anymore, but in HTML format, and also to go through the videos, because the videos shows you how the questions are answered in the homework assignments. All right. Counting is not going to be in the second exam. So counting is going to be in the final exam, but they're not going to be in the second exam. All right. So having said all that, I will show you exam 2 from spring semester. So I do want to make a disclaimer that there's no such thing as a quote-unquote standard test. I design my test in a way that I will test whether you understand the material and how thoroughly you understand the material, and to a certain extent, how quickly you can solve the problems. Okay, so speed is a concern, is one of the factors. I will not try to make a test so that half the class would run out of time first. Okay, that's not the design parameter. But I will design a test, okay, and grade accordingly, where people who can finish all the questions will score higher than people who cannot finish all the questions, everything else being the same. Because it is not just about whether a problem can be solved, it is also about whether the problem can be solved within the amount of time that I have given to the class. So that is, I just want to make this clear so that people do not come back to me after the exam and express that they did not understand that was how I plan, how I would plan to score the exam in the first place. All right, so having said that, let's go ahead and start with question number 1. This is obviously just in text format, and in the actual exam it would be more like what you see in exam 1, where things are more formatted, a little bit more polished, and so on. And also this time I might use a spreadsheet to collect the answers. So instead of only sharing one single document which has all the questions, I might also share a spreadsheet document so that people can put answers into the cells. That makes it more possible for me to use the script to grade the answers, which is a very important thing to me. All right, so let's take a look at this question. And if you think that you have not reviewed the relation material enough to answer these questions, you might want to hold off attempting the practice exam until you have reviewed the material, because the idea is you probably want to test your own knowledge. So for that matter, I am going to post the practice exam, on Discord. So this way you have a chance to read it first. All right. So now we get started with the content. Relation R is a set. Okay, we can tell because of the braces. It has 4, 4, 4, 3, 7, 7, and 7, 3 in this case, and it is defined a set, which is X, and it has 4, 7, and 3 as elements in it. So now I need to describe whether the relation is, the properties of the relation, whether each property is true or not. If it is false, I want people to point out why that is the case. In other words, what makes this relation R not blah blah blah, or whatever the blah 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 is. Alright, so let's take a look at reflexive first. So in this case, it is not reflexive. Okay, so we'll answer false first. And then for any answer that starts with a false, okay, we also need to explain why it is not reflexive. So now the answer itself has to be complete. It has to show me that there's an understanding of what reflexive means, and in addition, a concrete example based on this question that makes this particular R not reflexive. So in this case, I can say every element needs to relate to itself. Okay, so and I can make it even more clear. Every element in X needs to relate to itself. And now we say, okay, 4, 4 is okay, 7, 7 is okay, but 3, 3 is missing. So we'll say 3, 3 is missing. And that's basically what I'm looking for. Okay, an explanation, and also telling me why this particular R is not reflexive. So now we check out symmetric. It is not symmetric, false. And we will basically say because if AB is in R, then if and only if, okay, let me go back. So I'm quoting, a part of, the definition of symmetric. So AB is in R if and only if BA is in R. Okay, and then now we say, well, 4, 3 is in R, but 3, 4 is not. Okay. Now we look at asymmetric, and let's take a look at this. Is it asymmetric? And the answer is yes, it is. Okay, it is true that it is asymmetric. And if the answer is true according to this question, there's no need to point out why it is true. So we just say true in this case. Now this is the exam in spring 2020. It doesn't mean that the polarity of the questions are the same for yours. So you still have to read your question carefully, okay? But I'm just showing you what exam I used in spring. All right, so now we want to see whether it is transitive. So being transitive means, if AB and BC are in R, then AC should also be in R, okay? So now we look for cases where that is not true, okay? So we say false, okay? And then we quote the reason, okay? We quote, a part of the definition at least. So we say AB is in R and BC is in R implies AC is in R. Now we use this specific R to explain why it is not transitive. So we say 4, 4 is in R, 4, 3, oh, okay, that's not what I wanted to use, because 4, 3 is in R, so that part is fine. So as it turns out, it is transitive. Okay. So I have to go back and say it is true, it is indeed transitive. So now we have to ask whether it is comparable. Comparable means every element has to relate to every other element in a particular way. So so we can see how 4 is relating 4 to itself, 3 relates 4 to 3, but there's nothing here to relate 4 to 7. So now we can say it is false, okay? And the explanation is 4 does not relate to 7, meaning 4, 7 and 7, 4 are both missing. That is the reason why it is not comparable. Is it partially ordered? In order for something to be partially ordered, it has to be reflexive, and it is already not reflexive. So we can say false, it is not reflexive, and reflexivity. Yep, there we go. Is required. Okay, so it's important to point out that reflexivity is required instead of just not reflexive, because if people give me the answer of it is not reflexive, then I cannot tell whether that person thinks that reflexive is the only requirement in order to be partially ordered, or it is one of the requirements to be partially ordered. And to mention, in addition to not reflexive, and that reflexivity is required, means reflexivity is necessary for partially ordered, which also means that there may be other properties that are required as well. Totally ordered is also false because it is not partially ordered, and partially ordered is required. There we go. So the other two questions, are kind of the same. I can give you the answers to each one. So this one is pretty clear that it is not reflexive. We basically want to say for each E in X, EE should be in R. And in this case, 4, 4 is missing in R. Okay, so that's how I explain why it is not reflexive. In terms of symmetric, it is also false. We basically say, AB is in X in R, if and only if BA is in R. So in this case, we can see 4, 7 is in R, but 7, 4 is not. Is it asymmetric? It is asymmetric, okay, so it's true. Is it transitive? So this time we can definitely tell it is not transitive. And in order for a relation to be transitive, we basically have to make sure that AB is in R and BC is in R, implies AC is in R. So in this case, we can see how we have 4, 7 in R. We have 7, 3 in R, but 4, 3 is not in R. That is the explanation. Is it comparable? So we can quite easily tell, but just by the number of elements, that it is not comparable. But we also want to be able to explain why it is not comparable. So the explanation is kind of the same as before. We can just identify one of the elements that does not relate to some of the other elements, and we can take our pick here. 4 does not relate to 3, and in order for something to be comparable, every element is to relate to every other element. Okay, so we can also explain here, every element in X should relate to all other, no, all elements in R, including itself, in X. Sorry, there we go. And 4 does not relate to 3. So this time it is also not partially ordered, because partial order requires reflexive or reflexivity, and R is not reflexive, and it is not totally ordered. We say false. Total order is partially ordered, but R is not partially ordered. There we go. So that's a slightly different way to explain it, but it's gets the message across too. Okay, question number 3. Same thing. Okay, so you can see how once you read the first question, the format applies to the other 2 questions. I believe there are only 3 of this format. So once again, we have to answer the question, is it reflexive? And this one is clearly not reflexive. So we say false. And in order to be reflexive, we want every E in R to have EE in, the first one is in X. The second one is in R. And we can tell that 4 is missing. Okay, at least one is missing. Okay, you just need one thing to be missing for it to be not to be reflexive. Is it symmetric? It is not symmetric. False. Because in order for something to be symmetric, AB in R, if and only if BA is in R, must be true for any way to arrange the A and B. A has to be in X, B has to be in X, but other than that, this statement has to be true. So in this case, we can see that 4, 7 in R, but 7, 4 is not in R. Okay, and now we get to antisymmetric. And this one is not antisymmetric. This is false, because in order for something to be antisymmetric, we basically say AB in R and BA in R implies A equals to B. That's the definition of antisymmetric. Any way you can arrange A and B, A is an element of X, B is an element of X. Any way you can pick, the A and the B, this statement has to be true. So in this case, we can see that 7, 3 is in R, 3, 7 is also in R, but 3 does not equal to 7. So that is why it is not antisymmetric. Is it transitive? It is not transitive. Okay, there are quite a few reasons why we can say it is not transitive. You just have to pick one, but you also have to give me the reasoning. So you have to say AB in R and BC in R implies AC is in R. But in this case, we can see how 4, 7 is in R, 7, 3 is in R, but 4, 3 is missing in R. Okay, we can finish the sentence in R. There we go. Is it comparable? 4 does not relate to itself, nor does it relate to 3, so it is not comparable. Okay, so we say false. Because every element needs to relate to all elements, and we can see that 4, 3 and 3, 4 are both missing. 4 does not relate to 3. Okay. Is it partially ordered? No, because reflexivity is required and R is not reflexive. Is it totally ordered? No, because partially ordered is required and R is not partially ordered. There we go. Okay, now we move on to question number 4. Oh, okay, I lied. Question number 4 has the same format. And we'll now take a look at, is it reflexive? This one is quite clearly not reflexive, is it? Okay, so for every E in X, EE should be in R. And now we say 4 is not in R. There we go. Is it symmetric? Okay, so we start with 4 4 is there, 4 3 4 is in there, 7 4, and 4 7 is in there, 7 3 7 is in there. So it is symmetric. So we say true. Is it anti-symmetric? Clearly not. Okay, so we say false. And we quote the reason, because in order to be anti-symmetric, AB in R and BA in R implies A equals to B. But in this case, 4 7 is in R, 7 4 is in R, but 4 does not equal to 7. Is it transitive? And it is not transitive, false. Okay, and the reason, so quote the reason first. Okay, A, B in R. Okay, so if you don't like typing, and I know some of you are saying, okay, all this typing is taking extra time, then you can use a shorthand, okay? Because AB is in R, it's basically saying ARB, okay? That's a notation. So we say ARB and BRC implies ARC, okay? But in this case, we can see that 4 are 7 and 7 are 4, but 4 it is okay, you can use the exclamation point to mean logical negation, but not 4 are 4. So that's why it is not transitive. Is it comparable? False. Okay, every element in X needs to relate to all elements in X. And we can see how 4 does not relate to self. Okay, well, just make it very clear, 4 does not relate to 4. Okay, is it partially ordered? False. Okay, reflexivity is required and R is not reflexive. Now it is also missing a whole bunch of other requirements, but since they're all necessary requirements, that means if you miss one of the requirements, one of the conditions, it is not going to be partially ordered. So quoting just one of the properties is missing is enough as an explanation. Totally ordered, also false, because partially ordered is required and R is not partially ordered. There we go. All right, so question number 5 is in a slightly different format. This time I give you a set X and I want you to come up with an R that has certain properties. So this time it has to be totally ordered. It is also going to be symmetric. If no such R exists, explain why that is the case in terms of which property combined guarantees. Okay, there's a typo, guarantees. Okay, so it's supposed to be guarantees which other property cannot meet the stated requirement. Okay, all right, so let's think about totally ordered. Okay, so for something to be totally ordered, it has to be partially ordered first, and to be partially ordered, we need it to be reflexive. So we definitely are going to have 4, 4, 7, 7, and 3, 3 in it. It also needs to be anti-symmetric, which basically means, if we have 4, 7 in it, 7, 4 cannot be in it. Okay, and right there, okay, we find a contradiction, because if 4, 7 and 7, 4 are, cannot be both in R, and one of them has to be in R, then we know that it cannot be symmetric. Okay, but to explain that, okay, we kind of have to use a little bit of logic explanation here. And if you want to use proof by contradiction, now would be a good time to do that too. Okay, so either way, you have to use logical reasons to explain why it cannot happen. Okay, so we first state that total order requires partial order, and partial order requires anti-symmetry. So with anti-symmetry, let me see. Okay, so anti-symmetry by itself is not a problem, but when we combine anti-symmetry and comparable, means that 4R7 or 7R4. Okay, because 4 and 7, they have to relate in one way or the other. Okay, now anti-symmetry requires okay, let me explain this one kind of more step by step. Okay, so let's start with just comparable first. So delete all this. Comparable means 4R7 or 7R4, and this is just a regular OR, meaning that you can have one or both. Okay, so that's that's fine because it's just an ordinary OR. Anti-symmetry excludes, okay, 4R7 and 7R4 because 4 does not equal to 7. Because 4R7, if we have both, 4R7 and 7R4, then it cannot be anti-symmetric because 4 does not equal to 7. So this means we can have 4R7 or 7R4, but not both. We must have, okay, instead of can, it has to be a must. Okay, so you have to kind of choose your words carefully, because instead of can, you have to say we must have 4R7 or 7R4, but not both. This means 4R7 if and only if 7R4 is false, and as a result, the relation R is not symmetric. So this is an explanation of the contradictions or the restrictions within the relation has a problem. Okay, question number 6 is also in kind of the same format, and this time we want it to be not reflexive, we want it to be anti-symmetric, and it is not transitive, and is comparable, and it is not symmetric. Okay, so not being reflexive is easy, okay, because all we have to do is to make sure that we don't have oh, okay, let me fix this spelling first. Okay, so guarantees. All right, there we go. All right, so not reflexive is easy to meet. Anti-symmetric is also easy to meet. Not transitive is kind of easy too. Okay, it needs to be comparable. So it is not possible, because in order for something to be comparable, it needs to relate to itself. And that's the kind of really clear contradiction here. Okay, so we say in order for R to be comparable, each element of X needs to relate to each element E of X needs to relate to E. But since R is not reflexive, this requirement cannot be met. There we go. Number 7. So number 7 has the same format, and this time we want R to be not reflexive, we want it to be anti-symmetric, we want it to be transitive, we want it to be comparable, and we do not want it to be symmetric. So once again, we have not reflexive and comparable. So that means the same explanation is going to work here. I'm just going to do one thing to check the definition, because I have this kind of gnawing feeling that I might have contradicted my own interpretation of comparable. So let's go back to relations and check out what is comparable. Now the test is open book and open notes, so that means if you have any questions like what I'm having right now, you can definitely go double check. Alright, so totally ordered means it is comparable. So that means for every way to relate for every way to pair up E and F, we need to have one or the we have to have ERF or FRE, which means they can both be there or just one of them is there, but we need at least one of these two to be in R. So that means self-relating or reflexivity is required. So that means it is proper to answer question number 7 the same way as the other two questions. All right, so question number 8 and 9 and 10 and 11, those are all based on resolution. Okay, so they are all starting with a psi. So we have to translate psi into a CNF first. So we look at psi, and you have to remember what is a CNF. It's conjunctive normal form. So in this case, you can see that some of the parentheses are actually not required. So I am going to, I like it to be a little bit more concise without the extra parentheses. So this is the simplified form of it. And in CNF, we want a whole bunch of disjunctions connected by a final conjunction. So this is not quite there yet. Okay. So now we look at this and say, okay, how can we make it into a CNF? Now the trick to do this is we can see that there's a mini CNF here already, right? So this is already in CNF, and everything else are just ORed. So that means we can just use distribution to distribute the things outside of the CNF into the CNF. So just to remind you what is distribution, or which distribution we are using here, in Boolean algebra, okay, if you have A and B or C, this can be written as A plus A or C and B or C. So that means we can attach not P to both of these, to not Q and also to not P. So, and you can also apply simplification, because in a overall OR, Let's see, can you apply simplification? Nope, you cannot apply simplification, so I was wrong about that. Alright, so let's apply distribution. So once we apply distribution, then we have not P or not Q, and then we have not P or, oops, not P or not R, okay, and then or not R like that. And we can see that, hey, not P and not P cancels out. So it becomes just that. And then we can apply distribution again and distribute this not R into all of those terms. So we now can say this or not R, and then this or not R. Get rid of that. And now we do a little bit of simplification like that. And we can simplify even further, because in this case, when we have a overall conjunction, then we keep the most restrictive subterms, and in this case the most restrictive subterm is not P or not R, and that is our psi. And then we work with the proposed theorem. The proposed theorem is given over here. So now we have to say what is the negation of the proposed theorem. So we just put a big old negation, in over the original proposed theorem. So in this case, I'm just going to copy everything here first. Okay. Implies it is not the case that not P or Q or R. All right. So let me just check the parentheses. Okay, everything matches. All right, so typically the way I like to work on this sort of thing is to start with, oops, yeah. There we go. All right, so is to get rid of the implication. So to get rid of the implication, the implication itself becomes an OR, and we have to negate the expression to the left-hand side. And now we look at this. It is a pretty big mess, right? So we want to apply the Morgan's law, okay? Distribute the negation to the inside. So we'll start with this one. So it becomes a big conjunction. So you can do this any way you want to, but I just do in place like this. And then this one we can also use De Morgan's law. So by applying De Morgan's law, we end up with negating every single term inside the OR, and the ORs becomes ANDs. The outside or not is gone, and using the priority of operation, we don't need the extra parentheses anymore. And then finally, we can simplify the double negation, so it becomes just that. And we also have another simplification that we can perform here. So we need to now apply the outermost negation, which basically turns each one into a disjunction, and then we turn this disjunction into a conjunction. So with this one, I'm just going to rewrite the whole thing. So it becomes not P or not Q or not R, and not P or not Q or not R. And now we simplify the not like so, and we have a, oh, okay, forgot. Okay, so there are two nots here, 1, 2, and there's one not over here. So now we have another CNF. This other CNF is for not phi. Now we combine these two, so we have psi and not phi. And it's just a concatenation. So we take this and we take this and just make one longer CNF. And then now we try to use resolution. So there are quite a few ways to apply resolution in this case, because we can see that not R is here and then R is both here as well as here. So what I would do is I am going to clearly indicate which two I am resolving. Okay, so we'll resolve this one with, okay, let me make it more clear. We're looking at the not R, and then we are looking at the R here. So the result of this resolution is everything that was in the CNF originally is still there, but we add a new term, which is the concatenation of these two, but without the not R. So we have, without the R and the not R. So we have not P or not P or not Q. And obviously in this case, it simplifies to one single dot P, like so. And now we look at this and we ask, okay, can we resolve this any further? And the answer is, yep, we can resolve this further. So even if you can tell that there's no way we can resolve this entire thing, you cannot just say that, oh, this cannot resolve to a contradiction. But here, you have to show me that you get to a dead end. Okay. So the way I do it is kind of systematic. I use the first one and resolve with the third one here. So the not R and the R matches, and that's why we can apply resolution. And when we apply resolution, we basically just do a concatenation. So this time it's pretty easy. It's just not P or not P or Q, okay? But it does simplify to just not P or Q. So in other words, we just got rid of the R over here. Okay, so now we look at this and ask, can we perform any more resolution? And I typically just stick with the first term until I cannot do any further resolution with the first term, which is now. So now I move on to the second term and ask, does anyone have just Q? The answer is yes. Okay, we got both of these with just Q. So we now say, okay, we're gonna use not Q to resolve with this Q over here. So the end result of that is we are concatenating the those two, but with any mention of Q pruned out. So we end up with just not P or R. Okay. So we now look at this and continue to ask, can we do any resolution with this? So we see another term that can be resolved because there's not Q and then there's Q over here. Right, so there's but it doesn't give us any new terms, so it's not okay, let me explain what I mean by that. You can see how this term can resolve with this term over here, but when they do resolve, we end up with not P or R, and not P or R is already here. So that resolution doesn't give us a new term. And if we resolve this one with the last one, it also does not give us a new term, because all that does is to give us not P or R, which is already here. So we are running out of further possibility with the second term. So now we move on to the third term. So the third term is different from the second term because it has a Q, so it can resolve with anything that has a not Q in it. In other words, these two can resolve. But when they do resolve, we end up with not P or R, which is already here. So it doesn't give us any new term. This one does not resolve with this one over here, and it does not resolve with that one over there. So we are done with that one too. So now we look at the fourth term and ask, can it resolve with any of the other terms? The answer is yes. Okay, so the one right next to it, it can resolve because one has a not Q and the other one only has a single Q. So we say this not Q and this Q can resolve. So when that happens, oops, wrong place to paste. So when that happens, we have not P left, okay? Just not P by itself. And now we ask again, okay, can this resolve any further? Nope, it does not resolve any more terms. Then we look at this term here. Does it resolve it with any other terms? Nope. And now we ask, does this term resolve it with any other term? The answer is no. So now we are stuck, okay? So we are stuck in no further resolution is, I should say no further resolution result from this CNF, and as a result, phi is not a theorem. There we go. So that's how we answer question number 8. 9, 10, and 11 are kind of the same deal. So let's give question number 9 a try. So we first repeat here what is psi, and obviously you can use copy and paste. So, or you can just kind of retype the whole thing like what I'm doing right here. Not P, not Q implies not R, not Q. There we go. So some of the parentheses are definitely not needed. Like the overall parentheses, is not needed in this case. So the first thing we do is to apply the definition of implication. So now we negate the negation of not P, not Q, and we replace the implication with the or, and then not R, not Q. And when we look at this, we just know that we have double negation on the outside. So double negation cancels out. So we just get that much left. Okay. And this is the exact opposite of it's the exact opposite of CNF. This is a DNF. It's a disjunctive normal form, which is not what we want. Okay, so to and then what we can do here is to use FOIL, okay, which is a form of distribution. FOIL is basically distribution applied twice. So we can now say not P or not R, not P or not Q, and then we have not Q or not R, and then we have not Q or not Q. Okay, and then we can do a simplification with just not Q left here. And if you remember, we can apply even more simplification because in a overall disjunction, we can remove terms that are less restrictive. So when we have not Q already here, that is more restrictive than not Q or not R. In other words, if not Q is false, the whole thing is going to be false anyway. There's no need to evaluate blah blah not Q or not R. On the other hand, if not Q is true, then not Q or not R is also automatically true. So that means whether not R is true or not is actually immaterial. And that's why we can simplify and get rid of this. and we can also simplify and get rid of that, and that becomes the simplified version of psi. Now, if somebody asks me, do I have to do the simplification? The answer is no. Okay, you don't have to, because this is already a CNF. Okay, even though it looks really ugly, it's already a CNF. But the more simplification you do, that means you can save time when you have to deal with the resolution. So now we look at what is not phi. It is the negation of phi itself, right? So we look at phi equals 2, and let's see if this works. I'm trying to select which portion to copy and paste. There we go. It's just missing the end parenthesis, but otherwise that works. All right, so now we look at this, and the first thing we do, as usual, is to get rid of the implication. So, okay, I think it is better for me to line it like this. So this way I can just copy and paste to the next line. So we replace this with a, one too many deletion, with an or, and then we have to apply a negation to whatever was the left-hand side of the implication. And now we can apply De Morgan's law, and I'm going to apply De Morgan's law on both sides of the disjunction. So the overall negation is still here. We'll leave it alone. And now we have not P, not Q, not R. These are all connected by a conjunction. And then over here we have not P. Oh, this one is a conjunction as well. Oh, that's pretty handy. So not P, not Q is over here. All right. So now we can see that there is a simplification that we can do, which is the not P. So not cancels out like so. And now we can apply De Morgan's law one more time. And when we apply De Morgan's law this time, we end up with two disjunctive terms. And in the first one, we negate everything in the original conjunction. So we have not P or not Q or not R. And in the other one, we have not P or not Q. I personally like to keep the not, and then get rid of the not, once and for after the application of De Morgan's law. Okay, so now we end up with that. And I think that's it for not phi. So now we look at the overall CNF, so which is psi and not phi. So psi and not phi is just a matter of I think this time actually typing is faster. So let me just go ahead and type it. Not P or not R, not Q. And then we have not P or Q or R. And then we have P or Q here. There we go. All right, so, and as I said earlier, it's better to put it on a 9 like that. So now we want to say, okay, can we resolve? Well, there's a lot of stuff we can resolve here. So we'll take a look at this, and we say, this not R is matching this R over here. So we can combine those two. So we have not P, we just have to mention it once, or Q. Okay, there we go. All right, so now we look at this, and then we ask, can we resolve any more? Well, there are two terms there's one term with just P in it. So the P can also be used for resolution. And the P is mentioned here. So now we can resolve those two. And we just say we take Q out of the second one because I like to preserve alphabetical order. It kind of makes it easier to kind of match up things. Okay, so not R coming from the first one. So now we look at this one and ask, can we resolve this one? In terms of not P, we have exhausted everything that has a P in it. In terms of not R, we have a new term that has a not R here, which then becomes not P or Q, but not P or Q is already here. So we are done with the first term. Now we look at not Q and ask, what can we resolve this one to? It can definitely resolve with this one here because it has a Q in it. So when we resolve these two, we basically just have not P or R left. Okay. And now we look at this. We're still focusing on the not P, but we are asking what else can it resolve with. Okay, it can also resolve with this term here. So this Q and that not Q would resolve, right? So now we say when those two resolve, we have just P left. Okay, and you probably can tell that if we can somehow end up with just not P, then we are good to go. Or if we can somehow end up with just Q, we are also good to go. Okay, but I'm just going to do this systematically. So we look at this not Q again, and we say, oh, this not Q can also resolve with this Q over here. So not Q, and we have Q over here. So when those two resolve, we end up with, let's see, with just not P. Woohoo! Wow. Okay, so that is nice, right? I mean, because now we can say, well, okay, but we cannot stop yet, okay, because we have one last resolution. We can now say, hey, this P here is going to resolve with this not P over here, and the result of that is a 0. So now we can explain and say, since the CNF resolves to false, then using proof by contradiction, phi is a theorem. There we go. Cool. Then we have question number 10. All right, so question number 10, kind of the same deal. Okay, you just have to perform all the steps that we have performed with the other one. So let's go ahead and take a look. And let me see. I'm trying to find a way to, oh, I know how to do it. Okay. All right. I was just looking for a really fast way to select which portion to copy. And now we have it. And we just have to kind of turn it into a CNF. All right, so the outermost parentheses are unnecessary, okay? And we have not Q, not P, or not R in here, and then a not R out in the open like that. All right, so there's no simplification that we can do here because this has a not R, not P, but it also has a not Q ended with it. So it's not easy, you cannot do a quick simplification here. But since we have a CNF as a seed, we can grow the CNF because we can attach the other disjunction of items to the current CNF. So let's use the not P first. So we basically say not P or not Q, and not P or not P or not R. And then we have a not R on the outside, and you can see not P and not P is going to simplify out. And with this one, we just attach the not or not R to each one of the CNF already in the statement. Oops, there we go. And we can also see how we have not R or not R here, which means we can reduce it to just one single not R. And we can also see that this one is more specific because it doesn't have the not or not Q in it. So the one that is less specific, is not needed. So we can get rid of this. So the whole thing just simplifies to not P or not R. Now we look at not phi, and once again we try to copy and paste phi itself first. Alright, so first thing first is to get rid of the implication. And we can remove extra parentheses that are not needed. And right here we can apply De Morgan's law. So with De Morgan's law, we have not P, not Q, not R, or not P, not Q, not R over here. And then we simplify the nots. Okay, get rid of this. Get rid of this, get rid of this, there we go. And now we have a CNF. With a CNF, there are a few ways to, fix it. You can apply foil. So in this case, the foil is going to look pretty ugly, but it's a simple thing to do. Because the foil, basically in this case, we have a P or P, P or not Q, P or not R, we have Q or not Q, we have Q or not R, oops, Q or not R, and then we have P or R, yes, P or not R, sorry, everything is a not R, not Q or not R, and then we have a not R or not R. So now we can do some simplifications. Okay, so simplifications, you can also raise copy and paste. Okay, and this is why I think when it is handwritten, it's actually to me it is it saves time. Okay, just imagine you have to write all of this. That would be torturous. So get rid of the extra P over here. This is just 1, okay? So we simplify this to a 1, but since it's in the conjunction, the 1 basically just entirely, simplifies out of this whole thing. And then we are looking for more things to simplify, which is over here. This just simplifies to not R by itself. And now we can simplify based on which term is more restrictive. So P is restrictive, and then this entire term is less restrictive. This one is less restrictive, and this one is less restrictive. And now we have not R over here, and we can see that this one is less restrictive, and this one is also less restrictive. So not phi simplifies to P and not R. Okay, so now we look at psi and not phi, and that is just not P or not R, P and not R, and we cannot resolve any further. This one is already at a dead end right now, because if we resolve this one with P, we get not R left. So it's not a new term, so that step didn't help us. And then there's no further resolution. So now we can say the CNF cannot resolve to false. And so as a result, phi is not a theorem. There we go. And we are now getting to the last question. I'm looking at the time. All right, so this one is kind of the same deal. We have to convert psi to a CNF first. And let's do the same trick here. There we go. All right, so it's once again, it's a implication. We turn it to a disjunction first and get rid of the unnecessary parentheses, and then we get rid of the we simplify here because of double negation. All right, so that looks a little bit better, and then now we can apply let's see, distribution seems to make sense, right? So we there we go, we apply distribution, and we have not P Q or not PR or not QR. Let me check. Yep, okay. And now at this point we can apply the horrific foil, okay, or we can apply it twice, okay, we'll just do it twice. Okay, so the first foil end up with not P or not P, not P or R, and then we have not P or Q, and then we have not P or R. Yep, okay. And then we have the not or not QR on the outside. And now we can apply foil again. Basically, we're distributing these two into this whole mix here. So now we have not P or not, okay, so that's why it's good to simplify first, because if we simplify first, okay, let me do it on two lines so they can see what was the original. Okay, not P or not P is just not P itself, and it is a more restrictive term than all of the other terms that mentions not P or something, so we can get rid of the other ones. Oh, okay. So you can see how, quickly we simplify this to just not P by itself. Okay. I'm just looking at this to make sure that I did not make a mistake. Yep. It doesn't seem to make sense. Okay, I'll tell you why it doesn't make sense. Because in the original expression here, if Q and R are both false, then the whole thing is false. But what I simplify into is just not P, so that does not make sense. All right, so I must have missed something. Not P and Q, not P and R, and then I do a foil, not P. Okay, I know why. Nope. Okay, so we have not P or not P. I know why, because I was not careful. This one is supposed to be Q or R, not P or R. So I was not careful. So we do have Q or R left as a term, And then now we have to integrate the not Q into this whole thing. So we can apply FOIL again by treating not Q or R as well, okay, let me just kind of show you what I mean by that. So in this case, the distribution is A, B, or C is A or C, and A and B or C. Okay, so the AB is going to be this one here, and then we have to basically do an OR, and this is our C. All right. And then once we have that, we can distribute the OR into it. Okay, there we go. All right. So we have, so I'm gonna write it like this, and we're gonna replace this with an and then each one will just be ORed with one of the two terms, like so. And then we'll put extra parentheses around it first, like so that we can basically focus on each side. Okay. So the way I looked at this is to look at not Q as A, we look at R as B, and then we look at this entire term here as our C. So we basically just take this and then do an OR with one side, and take this entire thing and OR with the other one. And now we can apply distribution again, and this time we're just putting not or not Q into every single one of these, like that. Then we can get rid of the not Q or not Q on the outside, and then the parentheses become unnecessary at this point. And this one is the same thing. We distribute the not the or R into every single one in here. Then we get rid of the or R on the outside, and then this one simplifies, and also we don't need the outer parentheses any further. This one has Q or not Q, which simplifies to 1, and as a result, this entire term can go. And at this point, there's no further simplification. Now we get to not phi. Oops, not phi like that. And then we look for the phi definition, which is right here. Okay. And we copy the definition of phi down here, but we have to remember to negate the entire thing. And the first thing we do is to get rid of the implication, like so. And then we can, I think the easiest way to do this is to apply De Morgan's law, but the outermost De Morgan's law. So when we apply the outermost De Morgan's law, then we end up with, I'm just looking at all the negations here. We end up with not P or not R, and not P. And then the nots go away because they cancel out. Then we end up with that. And now we take out the term that is less restrictive, and we get just P left. There we go. All right, so let's do a sanity check to make sure that our phi is right. Okay, in other words, not phi is basically just it's the same as P, which means phi is really the same thing as not P. R does not actually R is not important in this case in any way. So let's double check, right? So if P is false, what's going to happen? If P is false, then well, not R can be true. And if not R is true and P is false, not false is true. So the whole thing is going to be true, because if P is false, then regardless of what this expression is the implication is always going to be true. So I just did a sanity check to make sure that the not phi is correct. All right, so now we look at the conjunction, which is psi and not phi. So that's just a concatenation of these two. So I'm gonna copy this here. I mean, that's just P by itself, so it's fine. There we go. So now we look for resolution. This one looks pretty promising, because we can, okay, let me get rid of that. Because not P is resolvable with this P over here, and that resolution will give us not Q by itself. Okay, just to emphasize that is by itself. And now we have to somehow, end up with either a not P is good, or we can have we can have a Q as well. All right, so but I can do this in a systematic way. And so we take a look at this, and let's see. Can the not Q resolve with anything? Yes. Okay, so we look at this not Q, and then we say that it can resolve with this Q over here. And as a result of that, we have not P from the first one, and then we have the R from the second one. Oh, okay, but that's already there, so this step is not productive. Okay. And I think we are done. I mean, there are no other resolution possible from only the first term. So now we look at the second term, which is this one here, and then we ask, do we have any mentioning of P? Yes. So we can look at this P, not P, sorry, and then we look at this P over here and say those two can resolve. And when they do, we end up with just R by itself. Okay. And oops. And now we look at this and go like, do we have any other mentioning of P? Nope. Do we have any mention of not R? Nope. So now we move on to this one, and this one can resolve with not Q, but we already have R as a result, so it doesn't help. And that's it. Then we look at this one here, cannot resolve, cannot resolve. Okay, so we are now stuck. Okay, there are no other further resolution ready available, and yet we are not at false. Okay, the CNF is not false. So we can say now, since the CNF does not resolve to false, phi is not a theorem. There we go. All right. So, I'm pretty much done at this point with answering all the questions while explaining. Okay. All right. So I will post this exam online, even though I just overwrote the original. Okay. I can always just regen it too, so that's fine. I'm just trying to think of, what to do from this point on. Okay, so I don't have a demonstration of a question for Aleph null, okay? So I will include that sometime later today, latest by tomorrow, so that you guys have a practice test for that too. On Thursday, we do not have a lecture because on Thursday we have a presentation from DISA, D-I-S-A. I talked about that last week a little bit. It's going to be I think it's going to be an interesting webinar. And as it turns out, originally I thought it was just ARC, just my classes. And now I think it's becoming a district-wide webinar. So we are expecting a lot of participants, at least watching it. I don't know whether we'll have time for a question and answer session, but since we know who are in the presentation, I'm pretty sure we can send them email messages to ask for more information. Anyway, I think we're done here. Okay, I think the recording is done, and I'm gonna attach. Okay, let me just kind of show you what I do when I look at the key here. So this is the key. It basically tells us. It tells us that it does resolve in question 11, so I got that one wrong. Okay. And the reason is psi is the way I resolve psi is not correct. Okay, so let's fix this one. I'm just going to follow my own steps here. Okay, so the QRR is still here. Oh, okay, you can see how this does not work at all. I got back to the original form. So now the distribution becomes the issue. We have the not Q, and then the other side has the R. And all right, so let's do this by hand one more time. Not P or not Q. Yeah, this one is Q or not Q or R. On the other side, we have not P or R. And then we have Q or R or R. All right, so now we simplify. This whole thing simplifies away. And this is becoming that. All right, so the key is telling me that psi resolves to not P or not Q, and then Q or R. So we got the Q or R, not P or not Q, and this term is the one that is in question. Not P or R. Is missing here, but it is in mine. Okay, so we have to ask, why is it there? So the not P or R is because of this not P being here. And this not P is here because there's a not P over here. And this not P is here because there's a not P because of the expansion. Okay, so this is the same as that. So let's just skip all the way over here. Oh, that is... All right, so let's double check. Okay, the way we can double check it is to make not P or R false and see if the original one would become false too. So we basically say, what if P is true to make not P false and R is false? Okay, in that case, the original one is going to be false. Okay, so P is true, not P is false. So the first part of the disjunction is going to be false. When R is false, the second part is going to be false. So there's nothing wrong with having not P or R in this expression. So the other reason is it can be simplified out. Okay, it is possible that my key itself is wrong. That is possible. Okay, how about not phi? Not phi is not P or not RP. And in here, I just have a single P. Okay, so we simplified out more than we should. Okay, so let's double check that. All right, so we have, let's see, double negation of not P or not R, and then double negation of P like that. And then we have the double negation canceled out. Okay, that's my bad. That was my bad. Okay. So with the first one, it is okay to have it like this. You know, there's a step of simplification that can get rid of this term here, but it is still in CNF the way it is. It's when I worked on the second one that I made a mistake because I got rid of because I forgot about the not P, and I just looked at it as P, and I thought that it would be a more general case compared to P, and that's why I got rid of it. Or I forgot the double negation of P becomes P, and it's not P that is left. So either way, that was a mistake of mine. So we have an extra term here, which is not P or not R. Okay, so that means we just have to continue with the resolution. Okay, right. All right. So we can have another resolution here. This R can resolve with this not R over here. And once that happens, we end up with just the term not P, and now we have resolved to 0. Let me point out what I'm doing here. We have this P over here, and then we have this not P over here. So those two resolve to 0, and now we come to a different conclusion. Since the CNF resolves to 0, phi is a theorem. Okay, there we go. So I fess up, I made a poo-poo here. I made a mistake. All right, so I think that should do it. All right, so the time is 8:30. I'm going to stop the lecture at this point, and I'll give you guys both the I'll give you two versions. I'll give you the one with the answers, and I'm also going to give you the one without the answers, so that you can work on it yourself. All right, so get this out. And I'm gonna post this to today's lecture. So there we go. I'm just looking at Discord at this point. I think I can stop the recording now.